heals pain. Yo, what's up, guys? Welcome to the stream. Hold on. Oh. Shit. Hello, my viewers. Hello. Welcome to the stream. Hello, yes. Hello, Stembo. Hello, Adam. Hi, Karweng. Thank you for joining in. Let's just wait for a few minutes. Tup. Let's go. Live now. Hello, bosku. Hello, Akmal. Good to see you. Good to see everyone. How is everyone? Korang dah makan belum? Aku tak makan lagi. Aku punya housemate baru nak masak. Dia baru habis masak. Tapi aku nak start dah. So, tak apa. I think it's gonna be about 2 hours, this stream. Depends on how long we're gonna do some exercises. I will, at the end of this stream, we will be doing some past years. Because none of I have not come over anyone yang dah buat past year. Okay, that makes sense. Hold on. Alright. So I hope you guys can watch my stream properly. Semua nampak kan? Semua dengar kan? Is the screen clear? Can you guys please answer me? Alright. Nampak and dengar. Alright. So, well, in that case, let's start our live stream. So, baca doa dulu. Allah Ta'ala inna wa ta'ala min khaza'id rahmatika amin. Alright. So, first thing, I will show you all of the topics that might ataupun most likely to masuk lah, because this is like there's a lot of content in one topic, but there are only certain subtopics that the lecturer actually discuss. So this is one of the most discussed topics in our course lah. So first is stress analysis. So that's the first one. And then we'll go to fatigue failure. Then we'll go to bearing. And then we'll go to lubrication. This lubrication and bearing is quite a tough topic lah, because there's a lot of considerations and also parameters that we are not used to. Bearings and lubrication. And then we have screw and fasteners. Screw, most likely we will be talking about power screws. Gear, we will be talking about spur gears. not really covering any other gears, which are like the helical or the pinion. So we're not gonna talk about that. We're just gonna talk about spur gears. Then we're gonna do welding, specifically on fillet weldings and the methods to solve the, what do you call, the stress, the stresses, the maximum stress, the allowable stress of weldings. Because there are two methods, the normal method and the parallelogram method. Alright, so it says here that I have a warning. I don't know, my bit rate is quite low, but never mind, as long as you have a good connection. Okay, so for the stress analysis, most of us are really familiar with this topic because we have been learning this since mechanic of materials. Yeah, basically another revision of mechanics of materials. So here is just a small table of the moment of inertia of a rectangle and a circle, a cylinder, as you may say. So, why does it always do that? Okay, so this is a rectangle for the about x-axis, about y-axis. There's no axis for circles. So J is like when the beam is rotating. So when the beam is rotating, you use J. So they have different polar moment of inertia for rectangles and also circle. Okay, so this is some of the diagrams of a basic rectangular beam, and this is like a I-beam or any composite beam you can call it. Okay, so first things first, there are two types of stresses that we're going to talk about: normal stresses and shear stresses. So normal stresses is they can be classified as axial stresses and bending stresses. So for the axial stresses, you have sigma equals to F over A, which is axial means along the shaft. So it's either you're pulling the shaft or you're compressing the shaft. So it's F over A. Bending is like when you want to bend your shaft, bend your pencils. So sigma is equals to moment times the distance to the neutral axis over the moment of inertia. So those are normal stresses. Shear stresses, first is the torsional. Torsional is like when you want to twist, twisting motion of the shaft. So it is torque time radius over polar moment. So as you can see, the torsional and the bending is quite similar. They both have torque, which is torque and max moment, which is both in Newton meters. Distance, C or R, and the polar moment. For bending, it is moment of inertia. For torsion, is J. So the next one is transverse stresses. It's like stresses specifically for like the area affected for I-beams, or like the cross-sectional area that happens over here. So those are like transverse. That's what they mean by transverse shear stresses. Okay, so how we usually solve the stresses is by using Mohr circles. So there's a lot of things that you can do with a Mohr circle diagram by using the parameters given, which is usually the shear stress X, shear stress Y, and also the tau XY plane, XY plane. So this is the radius. So this is the angle. This is the principal stresses. This is the average stresses. So this is just like a recap, because most of us are already aware of the Mohr circle. Is very basic. So this is like something new, or this is nothing new. So I'm sorry. So this is just like a representation of the three cases that we have every time we are gonna do a Morse circle. So this is like a graphical representation I've made by myself. So the first case is the 2D Morse circle is both in the positive region. Usually in our course, there would be two-dimensional, and then they will ask us to transform it into like three-dimensional, or usually they really just say that the shear stress in the x plane or the x-axis is 0. So usually it includes three-dimensional Morse circles. So these are three-dimensional Morse circles. Two-dimensional Morse circle is just one circle. So here are three cases of how you want to do your Morse circle, because usually if you want to save time, you want to know how does your Morse circle looks like. Some people just, okay, let's do a Morse circle. Where do we start? We start with a circle. But for an advanced, much more advanced approach, you should know how does the circle itself looks like, you know. So this is the cases that we have. This is literally all of the cases lah. So this is when both of the stresses are in the positive region. So this is case 1. So as you can see here, this is sigma y and this is sigma x. Both of them are on the positive side of the graph. Okay, so this is the second case where both of the stresses are in the negative region, which means it is in compression. So I don't remember. So the stresses would only be in tension or in compression. Tension positive, compression meaning negative. So this is where both of the stresses will be negative. So this is the third case is where the stresses, one is in negative and one is in the positive region. So this is how it looks like. So okay, so first, as you can see here, when both of the stresses are in the positive region, the xy plane or the xy circle, that's what we call it. This is the highlighted in purple. Is what we call the xy plane circle. It will be a smaller circle, and then there will be the much more smaller circle where the intersection is at the origin, because the stresses of z is 0. So there needs to be a circle intersecting at the origin. So that is how we do it. So usually you would want to draw a circle first with the xy plane circle, and then a circle intersecting at the origin. Okay, and then there is a bigger circle surrounding both of those smaller circles. Okay, so usually we would just plot it first. So we know that both of them is on the positive side. So what is the y direction of the coordinates? So the y direction of the coordinates is actually the tau, the shear stresses. The shear stresses. This is normal stresses. The shear stresses. The shear stresses. So we have assumed here, we assume here that all of these cases are counterclockwise. Counterclockwise means that the shear stresses are negative. If it's clockwise, the shear stresses are positive. Okay, so kalau pernah nampak, if we usually answer, the Morse circle is usually given like a plane element, then there's like a square, and then at the top corner of the square there will be like shear stresses. So if the top one is facing if it's like this, it means that it is clockwise. If it's like this, it means that it's counterclockwise. CCW, this is CW. So that corresponds to the shear stresses. So the shear stresses would be negative for counterclockwise, and shear stresses would be positive for clockwise. So we also assume in these cases that the normal stresses for X is bigger than the normal stresses in Y. Okay, so that's just assumption we do, so that it is uniform over all of the three cases. And then we of course assume that the normal stresses the normal stresses for Z is equals to 0. Okay. Alright. So from there, we know that the shear stresses are negative. So if it's negative, the angle should be downwards, downwards from the x-axis. So this is the 2 phi, the 2 phi, or the principal angles. Okay. So okay, that's it lah, basically. So usually what you want to find in a Morse circle is usually the maximum shear stresses. So this is the maximum shear stresses for the xy plane, but because we have a bigger circle surrounding the xy plane and the yz plane, we have a bigger circle which is the xz plane. So the xz plane is actually the absolute maximum shear stress. That's what we call it. So this is the absolute maximum shear stresses. Usually the one with the biggest radius. Okay. So how you find that is just usually just find the radius, find the radius of the xy plane, and then macam tambah, add with the diameter of the smaller circle, and then you would just find the diameter of the whole bigger circle, and then just bagi dua. Macam tu lah. I think you guys are smart to do that. So that's how we just find the maximum or absolute shear stresses. Okay. So that is the positive region. So for the negative region, it's just like a mirror image where you have the the normal stresses of Z intersecting at origin over here, and then both of the normal stresses of Y and X is on the negative region. So the XY plane would be a small circle followed by a smaller circle, and then there would be another bigger circle surrounding it, would be the YZ plane. So also the absolute maximum shear stress is carried by the YZ plane. Okay. So for the third case, where we have both of the normal stresses in the negative and positive regions, we would have the XY plane to be the biggest circle. Hi Zad. So the biggest circle would be the XY plane. So it's different from the other two cases, where the two cases the XY plane is smaller, but this one is the biggest. So the absolute maximum shear stress is equal to the maximum shear stress of the XY plane, which is the radius of the XY plane of the circle lah. Okay, so that's all. So one more thing that I want to share with you guys is that the principal stresses, when you find the phi p, it's actually when you like the formula is phi p plus phi s equals to 45 degrees, because usually in the Morse circle the angle would be double in real life, would be double in the Morse circle, but in real life it would be half of it. So if the angle is 90 degrees in the Morse circle, in real life it should be 45 degrees. So usually we, in the Morse circle, we find 2 pi, but in real life you just want to find pi. So usually what we have here is that 90 degree equals to 2 phi plus 2 phi p plus 2s. Macam tu. S2 is the angle, is over here. It's like this angle over here. This is this is S. So what does that represent? It represents the maximum shear orientation. Okay, so now we move on to the plane transformation. This is also in last semester's mechanics of material. So there's shear stress, or the usual we find in the questions. And then if they want to transform the plane, you would have usually a principal stress orientation where the shear stress is equals to 0. So it means that we are plotting against sigma 1 and sigma 2. Sigma 1 and sigma 2. Yes, sigma 1, as you can see here, sigma 1 and sigma 2. So the angle of each you have is equals to the principal angles. That is why finding the principal angles is important. But there's also one more orientation, which is the maximum shear orientation, where the shear stress is maximum. So the normal stresses are both equal. So it would be average, the average stresses. So it will be equal for the XY plane. So this angle is phi s, which stands for shear. Okay, so that's all about you need to know about stress analysis. So it's just like revising through mechanics of material. So now we go to fatigue failure. But before we go to fatigue failure, is there anyone having any questions for stress analysis? You guys can put in the chat. You guys have any questions for stress analysis? Amir, kenapa cakap nama je? Ada soalan tak, Amir? Tak ada soalan, tak apa. Okay. Thank you, Amir. So far so good. Alright. So now we go to fatigue failure. So what is fatigue failure? Is when a part is introduced with stress over and over again until it becomes fatigue and it fails. So it is what this study is called fatigue failure. Okay, so usually it has an endurance limit. So one of the things that we first learn in a fatigue failure topic is the endurance limit. Endurance limit, there's a simplified estimation where SE is the strength, S represents strength, E is the endurance limit. Okay, so it is simplified that SE prime equals to 0.5 SUT if the SUT stands for ultimate strength. The ultimate strength is usually found in the property table, is under 1400 megapascals. Above that, the endurance limit would be 700 megapascals. Okay, so from the endurance limit, we also want to find the marine factors. So usually, the thought process goes to, you have a material. Amir ada tanya, for the third case, safely assume if sigma 1 and sigma 2 given, can we assume that that the third sigma is 0? Okay, so dia ada beza tau, sigma 1, sigma 2, sigma 3, sigma X, sigma Y dengan sigma Z. So usually dalam soalan, you would label principal stresses as sigma 1 and sigma 2. So sigma 1 would always be bigger than sigma 2. So kat sini kan, kalau korang perasan, sigma 1 always in front. Sigma 1 followed by sigma 2 followed by sigma 3. It doesn't matter if it's X, Y or Z. So this is also sigma 1, sigma 2, sigma 3. So this one is sigma 1, sigma 2. This is sigma 2 over there. You should zoom in. And sigma 3. So Amir's question is that, can we assume that the third sigma is 0? So if you want to assume the third sigma is 0, usually is the first case. First case, third sigma is 0. For the second case, the first sigma is 0. For the third case, the second sigma is 0. So this is 0. Why is it considered sigma 1? Because the other sigma, it has negative values. Okay, so that's what they usually do lah with the values of sigma 1, sigma 2, sigma 3. So those are called principal stresses. So principal stresses is also considered maximum stress or minimum stress. Okay, so Akid, hi Akid. Last paper. Esok last paper kid. Last paper for my second year. So quite excited lah. Tak ada excited. It's actually quite a killer subject lah. Oh, ikut case. Alright. Thanks a lot, Nasir. Alright, you're welcome. So right now, usually, if you are given a material, you would find its ultimate strength. So from the SUT, you see if the SUT is lower or higher than 1400. If it's lower, usually it is, you would go for the first condition. SE prime equals to 0.5 SUT. So if the SUT is, for example, 100 megapascals, so the SE prime would be 50 megapascals. So how do you want to find the endurance limit? So the SE, this is the SE prime. This is the SE. SE prime is like the test specimen of endurance limit. So this is how we find it is using marine factors. So we have Ka, Kb, Kc, Kd, Ke, Kf. Okay. Alright, thank you, Kate. So there are, all of these K's are like coefficients or constants, if you might call them. So all the constants are usually given. So usually given, and they have like one equation for each table. So okay, let me explain that. So Ka, we have surface condition. Kb, we have size factor. We have Kc, load factor. We have Kd, temperature factor. We have Ke, reliability factor. And we have Kf, miscellaneous modification factor. So for the first factor, usually Ka, we call it surface factor. So there's Ka equals to A dot SUT B. So usually in the table, it will give you the values of A and B, which is also constants. So you would see the surface. It's talking about surface. So the table should contain surface properties of the material. If it's machine, or is it hot roll, cold drawn. So this is the A and this is the B. So all you need to do is just plug in. You know, design machine. In this course, the values are always given, but you always need to know what to key in and how to use it. So that's the most difficult part, because there's so much things to input. So sometimes we become very confused. But if you really understand what you want to do and how you want to do it, it will become easier. So by breaking it down, you understand it much more better lah. So this is the size factor. Size factor Kb in mm. Size factor doesn't always has this. The factors are all dimensionless. If you can understand, dimensionless. Selalunya memang semua dimensionless. Okay, so Kb equals to 1.24D kuasa 0.107 for a specific range. So usually they have a specific range lah. So there's also an equivalent diameter. So size factor, dia ada dua. Dia ada Kb yang you would just find straight up from here for a rotating and round shaft. But sometimes the column or the shaft is not rotating. So you want to find an equivalent diameter if the shaft was rotating. So that's why it is called equivalent diameter, DE. So you need to add another step to it to find DE, which is 0. Either it's circular or either it's rectangular. So that is size factor. The bigger the size, I don't know what. Maybe the bigger the size factor. I think so. Okay, so we have load factor. This is quite easy. It is specific for different types of stresses: bending, axial, and torsion. Okay, so we have temperature factor next. ST over SRT, which is also given in a table. This is just a short snapshot, just a short picture of the table. There's the table goes much more longer, but usually if it's operating at room temperature, it will be atas ni lah. Okay, so there's reliability factor KE. Usually reliability factor ni orang guna 50% ke atas. Orang tak guna 50% ke bawah. Okay, so and then we have miscellaneous factor, which we assume to be equals to 1, because there's nothing saying about that in the textbook. So yeah, we just assume it to be equals to 1. So next we have fatigue stress. Okay. Fatigue strength. Fatigue strength are also known as SF. SF equals to F times SUT. So SUT is ultimate strength. Okay, so we have, okay, let me see. We have a SN diagram equation. Okay, so okay, we have stress concentration. Okay, wait, hold on a minute. SE, okay, SF, fatigue strength. So usually they would ask you to find endurance limit and fatigue stress. So both of them have different methods of using. If you want to use the endurance limit, you use the marine factors. If you want to use the fatigue strength, you use the SF equals to F times SUT. It's quite straightforward actually. F. Oops. Okay. So okay, so SN diagram. Oh, saya terpadam je. SN diagram ni, S refers to the stress or the strength, N refers to the number of cycles. So I think you guys can imagine it. So okay, so usually you have like, what do you call this? Polynomial. Tak ingat lah. Logarithmic, something, I think it's a logarithmic equation. SF equals to A times number of cycles kuasa B. So A ni ada their own equation, B ni pun ada their own equation. Okay, so N is number of cycles, and then reverse stress. So usually if they want you to find the fatigue stress, you would put the SF as the, kata apa, penyebut kat depan on the left hand side lah. But if they want you to find the number of cycles, usually find the number of cycles until failure, and that's what they usually say with this given strength or with this given stress. So this is the equation that you want to use. So N equals to sigma, also known as the reverse strength, or also known as like the reverse fatigue strength, over A times kuasa B, macam tu. Okay, so now we have design factor ni. Design factor, there's a lot of design factors, but like there's modified Goodman, there's Goodman, there's Soderbergh, so ada lagi banyak, ASME ada, but this is the usually the most widely used design factors. So sigma over SE, sigma M over SY equals to 1 over N. N is the factor of safety or design factor. Okay, so usually if it is equals to 1, we assume it to be safe lah. Above 1 is much more safer. So if you apa, macam mana cakap, you know you're doing the right thing if the factor of safety is more than 1. Yes, that's the right value you should get. If your factor of safety is lower than 1, there's something wrong with your design. You need to change something, or you did a mistake. So usually factor of safety must be more than 1. So that is what factor of safety means. Okay, so this is alternating stress, this is mid-range stress, this is endurance limit, SY is the yield strength, SUT here is the ultimate tensile strength. So there's a difference between the difference between Soderbergh and Goodman is that for Soderbergh there's yield strength, for Goodman there's ultimate tensile strength. Okay, so what is mid-range and what is alternating stress? So we come to the fluctuating stress. So fluctuating stress is, for example, the material given, it is sometimes is compression, sometimes tension. Macam tu lah. Sometimes it loses stress, sometimes the stress increases sinusoidally. Macam tu. So there are 3 types of fluctuating stress: general stress, repeated stress, and reverse stress. General stress ni is like the sine graph above the apa x axis. This is called the time lah. Time, where what we usually time macam mana, time over time. Yelah, over time, kalau benda tu selalu jadi in an hour macam tu. Sekejap, dah merepek. Okay, sabar. Ulang balik tadi. General stress. General stress, dia punya sign tu atas x-axis. Repeated stress ni, dia punya minimum dia betul-betul atas x-axis ni, which is sigma mean equals to 0. That is repeated stress. Reverse stress is that the graph is both in the positive and the negative region. So for example, it's in compression and tension all the time. It just plays back and forth. Okay. So mid-range is like the average of the stress. For example, the mid-range of this is the maximum minus minimum, so you will get the average. So that is what mid-range stands for. Mid-range for the reverse stress is equals to 0. The alternating stress, alternating stress is the distance between the amplitude and the mid-range stress. So it's over here. So sigma A is the distance between the mid-range and the amplitude. The mid-range stress is the distance, is the average stress. Then this is the maximum stress. This is the minimum stress. Macam tu lah. Okay. So next we have stress concentration. Stress concentration, there's a lot of designs lah. A lot of designs. Contohnya, dia bagi kau shaft, and then there's like a fillet. So there's too much graphs, there's too much diagrams to be included in these notes. So this is just the most important thing that you want to know for stress concentrations, because in design machine, we want to avoid stress concentration so that your part does not easily fracture. So if it's sharp, it's more prone to failure. But if you introduce a fillet on the surface, so it would be more unlikely to fracture. So that is why we introduce notches, fillets. So we want to reduce the stress concentration. So there are a lot of stress concentration designs you can see in the textbook. So this is usually what the formulas give. Notch sensitivity, concentration factor. This is given for bending or axial loading. This is given for torsional loading. So KF ni is there's a difference. That's what I want to talk about. There's a difference between the miscellaneous factor and also the concentration factor, because the concentration factor is with a capital K. The miscellaneous factor is with a lowercase k. So I got that wrong during the midterm. So something I learned lah, because this is a lowercase k, this is a capital K. Okay. So for Q equals to 0, if there's no notch sensitivity, the KF will be equals to 1. But if there's a notch, for example, the Q equals to 1, the KF would be equals to KT. KT means apa? Tak ingat lah. Need to check back nanti. I don't remember what KT means. So it also says here, for any parts or any materials using cast iron, the notch sensitivity is always 0.2. Okay. Because cast iron is uniform, the grain the grain size of cast iron is usually uniform all over the part. So we can assume that the knot sensitivity is just equals for any type of shape of design. Okay, so that's all for fatigue failure. Do you guys have any question regarding fatigue failure? If you guys have any question, you can put in the chat. Okay, so it looks like we don't have any questions. We'll continue to bearing. Okay, so there's one past year question regarding on bearing I would like to show you. So this is one question regarding bearing. Okay, so you guys read this question and then you tell me if you guys understand or not. Okay, so so I assume you guys dah revise kan. This is a night before the finals. Of course you guys must have read something about bearings. So this is just a apa revision or recap. So this is one of the past year questions in 2022, last year lah. So the working parameters is 2 kilonewton as a load, 5 kilonewton radial load. Inner ring rotates at 400 rpm. Then it gives you a table. For some reason you don't know what the table does. And then be careful of selection on the appropriate roller bearing types. So this is one thing about design. Dia suruh kau propose a design. Macam ni. Dia suruh kau pilih. Make a careful selection of the appropriate bearing types. So not only do you need to calculate, but you also need to find the correct design that suits your use case. Okay, so Arif here says, I'm worried if tomorrow they will use unit like KPSI and inch because most of the graph given in the textbook use those units. So thank you for your concern. If they give graph in KPSI or inch, usually the equivalent metric units is on the above side. For example, let me show you. Where do you find a graph here? So this is the textbook. Hold on. Is there any graphs here we can see? So that's one graph. Mana lagi graph? Wait, do we have graphs in our notes? Let's just check. I think we have one. No, we tak ada. Okay, I think we'll come across later lah when we find more graphs. But kita belajar dalam matrix, so probably we will just use matrix also lah. Jarang lah orang guna inch and foot pound and also KPSI. Kalau tak aku bantai lecturer. Tak adalah, gurau-gurau. Kalau ada lecturer tengok ni, saya minta maaf. Okay, so now we masuk bearing. Sekejap, tadi tak habis tengok lagi soalan tu kan. Okay, so dia bagi kau Webull parameters ni. Webull parameter tu apa? So dia bagi kau coefficient A, B, theta and XO. Okay, so what is that actually? So actually dalam ni kita akan belajar something about probability. So the probability of the part to fail at what percentage. So that's basically it lah. So one thing we learn in engineering materials is that we cannot actually like calculate when will the part fail. It is usually given in a probability chart, or there's an area of where it is estimated or highly likely to fail. So that's not a fine line. It's usually a scattered line and usually it's just an estimation, and we use probability to solve it. So probability, why we use probability? Because it can show us how much percentage of it can fail. Macam tu lah. If you are given 100 pistons at this stress, only one piston will fail. So that means that the probability of the part to fail is like 1%. So that's how it works lah, basically. So that's why usually in failures or like in apa orang kata, apa atas ni, endurance limit, usually dia memang bagi macam an area of the graph. Dia tak bagi line macam tu terus. Dia bagi in a probability chart. So we will learn about that in reliability. So bearing ni, okay, kita masuk bearing dulu. So what is a bearing? Bearing life. Bearing life tu apa? So this orang kata keywords. These keywords are actually very important for you to understand the question. So dia bagi tahu life tu apa, rating life tu apa, median life tu apa. Dalam exam kau baru nak pening, ada life apa sebenarnya. So this is the few terms that you actually need to know or need to be aware of, because there are like a lot of terms in bearing. Like loading rate ni ada 4. Ada catalog rating, basic rating, static rating, equivalent radial load. So you guys need to macam consider getting to actually understand the terms. So over here we have bearing failure. Bearing failure means spalling or pitting of an area of 0.01 inch squared. Spalling or pitting mean dia macam besi tu dia rosak. Macam tu lah. That's how I can say it. Life is the number of revolutions for failure. Usually is in hours or in RPM. So there's a difference between life in hours and life in RPM. We will talk about that later. And then we have rating life. Rating life, life required for 10% to fail. Like I give the analogy tadi, we have 100 pistons, one piston fail, and all of them are given the same stresses. So that's 1% to fail. Now we have 10% to fail. So that is rating life. And then a group of bearings, a set of bearings macam tu. So this is also called the minimum life. Then we have median life. Median refers to the median, like the dead center of a probability chart. So that is what we call median. So median life is an average life required for 50% of it to fail. So for like we give a piston analogy tadi, we have 100 pistons at a certain stress. 50% of the pistons will fail. So that is the median life. Okay. So it's also called as average life. So if you guys don't know, now you know. Okay. Then we have loading rate. What is loading? Loading refers to the force it is acted upon. Macam tu lah. So kalau bearing ni ada force, usually it's either axial loading or combine axial loading, or I don't remember. Sekejap. It's either axial loading or bending loading. Tak ingat lah. Kita balik. Axial loading and radial loading. My bad, sorry. Radial loading and axial loading. Okay. So loading. We have catalog load rating. A constant radial loading provided by the manufacturer. So if you are given a graph, the catalog load rating will be given the C10. C10, that's like the minimum. C10, 10 refers to 10%. So the catalog itself refers to what the manufacturers provide. So that gives you a hint of what catalog load rating means. Then we have basic load rating. Basic load rating is the catalog load rating at rating life 10 to the power of 6 revolutions of inner ring. 10k RPM lah basically. Revolutions. So that is basic loading, or C. C is also given in a table because it is related to the catalog load rating. Then we have static load rating. Static load rating, CO, refers to the permanent deformation at the most stress contact. At the most stress contact. Usually what you in a part you can find the most stress contact usually like orang kata journal ke, dia akan stress dia akan lagi tinggi pada area lain, macam tu. So static load rating refers to when that certain point has or not has or reach permanent deformation. Okay. Then we have equivalent radial load. Equivalent radial load is the constant stationary load applied that gives actual life. Actual life refers to apa dalam textbook tak ingat lah. Tapi what the main thing you should focus here is the stationary load applied. Okay. So that is the equivalent radial load. There will be let me see, FE ada ke soalan FE. Okay, that's here. Okay, ada ni FE. Okay guys, tenang. Okay, now we go to kita nak pergi mana dulu? Reliability. Okay, reliability. So now we have reliability. So like I mentioned, you cannot actually predict precisely when the part will fail. So usually you do like a probability chart, or in this case a distribution, which specifically refers to the name is Weibull distribution. So this Weibull distribution is a specific formula you use. RD is the reliability, exponent is e to the power of negative, and then this is the equation xb minus xo, theta minus xo, and then there's b. Okay, so what is x? X refers to the percentile. Okay, in a probability chart, x represents the percentile. So this is 50%. Macam tu. As simple as that. XO ni is the minimum value of x. So this is XO. Macam tu. XB is the studied, macam the percentile that you want to look for. So that's it lah. So you will learn probability in design machine also. So the more you know. Okay. So B is a coefficient, we call it a shape parameter. And then XO ni minimum value, theta is characteristic parameter, and then we have XB. XB is the dimensionless life. Dimensionless life. And then this is the equation. Equation ni datang daripada sini. It is actually derived from the Weibull distribution. As you can see here, ada guna ln RD kan. So this is referring to the reliability lah. Theta is character over here at 0 semua tu. So what we want to find is the XB lah. XB RD. Okay. So that leads us to our next equation or next derivation, which is load life. So load life, also known as load rating. So what is it? So this is where where the apa, where the forces come in. Ni kita tak nampak lagi kan forces dia. Tak ada F ke, tak ada moment ke. Ni baru nampak F dia. Okay, so this is load rating. So C10, we discussed tadi C10 tu apa, is the catalog constant. We assume it to be equals to the rating load. Rating load refers to the forces, and then we assume it to be equals to the FD, design load times, this is the whole thing lah. So you want your design load to be lower than the rating load. Faham tak? Rating load tu is like the macam ni, the rating load is like the force that the manufacturer rates that part. For example, you have a suspension. This suspension is rated for 50 kilonewtons. So that suspension can only be used for structural designs or like cars that encounter below than 50 kilonewtons. So that is what rating is for. It tells you the characteristic of the certain part, macam suspension ke, engine block ke, chassis ke. But in this case we are talking about bearings, because bearing is like the most used element in machines. So that is what rating is for. It's like telling the person this is the characteristic of the part. Macam tu. So you have the design load. Oh shit. Okay, you have the design load. Okay. So you can darab dengan LD over LR. LD is the design life in revolutions. There's a difference between life in revolutions and life in hours. Okay. Then we have LR, rating life. Always remember that design life is on top, rating life is on denominator, because rating life is usually much more bigger. And then we also can say, we can also derive that LD, I hope you guys are taking notes, LD is equals to this fancy L and then ND times 60. This fancy L is called design life in hours. And then N is the rotational, the angular velocity, or what you want to call it, RPM. 60 is just because it is in hours. RPM times 60 will be revolutions per hour, times hour, you just get the revolution. So makes sense. So okay, that's R. So that is the difference between design life in hours and design life in RPM, in revolutions. Not RPM, revolutions. Okay, so 1 over A, power 1 over A. A is just a constant, just a coefficient, where if it's ball bearing it is 3, if it's roller bearing it is 10 over 3, which also approximately equals to 3.3333. So we need more for roller bearing. Okay, so this is radial and thrust. Hold on, this is graph plot. Okay, so far okay guys. Okay, so this is the graph of reliability. RD is the reliability of the design. That's what the D represents. Okay, RD, D stands for design. Okay, rated line. Okay, so this is the graph. So usually with this kind of graph you will find the what, the kecerunan, the gradient. The gradient will always be the same. It's just the magnitude of the graph tu berapa banyak. Korang faham tak? Dia punya gradient dia sama. So when the gradient dia sama, we assume that the gradient, which is FL times 1 over A, is constant. Okay, so from there we can assume that, hold on, we can assume that FB, FL, L is live, FL P 1/A equals to, contohnya FD L, this is not L bro, LB 1/A, macam tu. So that is what they assume to be, because the gradients are always the same. So this is the constant that they are referring to, and then they simplify it, they make it like this. So this is L, this is X. What's the difference? So X is dimensionless, L is live in hours, macam tu. So usually you want to use dimensionless because it would be more uniform lah, dia punya macam mana, increment tu much more uniform for dimensionless. Kat sini dia banyak guna dimensionless parameters. Nanti kau tengok parameter Petrov ni ke, Petrov ni ada banyak dimensionless parameters, lubrication ni. Okay, tak apa, kita tenang. Okay, so this graph is called the reliability graph, and then as I said, the gradients are all the same, just the magnitude where the graph is, and then we can approximate. This is what they come up with. So C10 catalog equals to FB. FB is the, hold on, what is FB? FB, don't remember. Okay, never mind. And then we have AF. AF is the application factor. FD is the, FD apa pula design design load. FD is the design load. Okay, and then we have X, XD, XO plus theta minus XO 1 minus RD over 1 over B 1 over A, macam tu. So usually they would give you the values of A, they would give you the values of theta, they would give you the value of XO, they would give you the values of AB, macam tu. So all you need to find is either the FB or the FD or the RD. Okay. Kalau dia kata reliability at 90%, RD equals to 0.9. So that's what it means lah. So this is combined reliability, means you have two different bearings, one on each end, for example, and they have different reliabilities. So you want to have the combined reliability, you would just have a product of them. Okay, so that's it over there. So over here kita masuk the graph for radial and truss. Okay, so there's dimensionless parameters. For the y-axis, it is the equivalent radial load. Equivalent radial load, kalau dia bagi radial load dia 5 kilonewtons, 5 kilo FR kat bawah, 5 kilonewtons macam tadi, dia akan letak kat bawah ni. Okay, so this is the equivalent radial load. Radial load, this is axial thrust FA. This is the radial load juga ke? Radial load juga radial load juga. Okay, V is the rotation factor. V is given over here. V is equals to 1.0 inner ring, 1.2 for outer ring. So this, because this graph is like divided into two sections, the one with where it's constant and then one where it's linearly increasing. Usually people would just call this low cycle ke? Low cycle, I don't think so, I don't remember. Bawah E E represents, if this is dimensionless load, low load. This is where higher loads. Alright. So because you don't know what this is actually a measure for dimensionless force. Okay. Because you divide equivalent load and radial load. Okay, so that is the axis is actually dimensionless force. Okay, so over here, so this is equals to 1 if it's less than E is always given, and then this is always above E. The dimensionless load tu dia akan bagi. Okay, so that's all for bearing. Okay, do you guys have any questions for bearing? Any questions for bearing? Bearing. Do you guys want to try and do this? Okay. So it is given that the axial load FA equals to 5 kilonewtons. FR equals to radial, 2 kilonewtons, 5 kilonewtons. In a ring rotates at 400 rpm, 400 which is n. N is number of cycles, RPMs are n kecil. N kecil. Beza n kecil dengan n besar. N besar number of cycles, n kecil RPM. Okay, hope that helps. So this is 400 rpm, 400 rpm. If you guys want to do this, yeah, you guys can. It's past year 2022. Then there's table 11, which is over here. Let me show you. This is table 11.1. This is table 11.2. Okay, kalau tengok sini, dia bagi tahu E tu berapa. Dia akan bagi tahu korang E tu berapa. So jangan risau. Okay, so ni kat sini korang akan dapat macam-macam lah. Tapi yang penting is which kind of bearings you guys are choosing. Either is a deep or an angular. So from there you will get the catalog rating, and you will get the what is CO? Basic load. Am I right? Or am I wrong? Static load. CO is static load. That's where permanent deformation occurs. Okay, C10 is catalog load. Okay. Okay. Bore. OD. Width. So this, you know what these are? This is the design of the. Kau ada buat soalan tak? Untuk soalan bearing tu, tak silap aku boleh tengok solutions manual 1121. Alright, thank you. Aku ada solutions dia. Ni. What is this? This is 6. Oh, this is only 10. 1121. Okay. Thank you, Ami. Okay, so kita buat sama-sama. Oh, lah, sebiji juga lah. Sebiji. Okay. So, okay, sekejap. And then dekat situ FA over CO is less than 0.08. Ruler bearing types, then provided Weibull parameters, A equals to 3, B equals to. Cuma I don't know the question macam lack some info, macam bore. Oh, tak, dia lack info sebab dia suruh kita pilih bore tu kita nak berapa. Faham tak? So that's why this question is quite hard, because you don't know where to set the bar or where to set the the table, because you need to decide on your own what kind of bore you want to use, macam tu. So usually finance dia memang macam tu tu, susah tu. Kau kena come up with a proposal, or not a proposal, come up with a suggestion. I want to use this type of bore because macam tu. Okay, B equals to 1.83, and then we have theta 4.459, and then we have x 0.02. We bool, this is FA over CO. CO is the static rating. Okay, this is used primarily to find suitable bearings. Okay, so that is what we know. Okay, so what is the next steps? So dia choose 30mm bore, C10 equals to 19.5 kilonewtons and C2 equals to 10 kilonewtons. Why? Okay, so dia kata apa FA over okay, jap, FA dia berapa? FA dia 2 kilonewtons. So CO dia kena cari somewhere there. So okay, FA equals to 2 kilonewtons kan. So we put there, and then we find CO, and then we put here 0.08. So CO is lebih kurang 2000 bagi 0.08, which is also lebih kurang. Am I doing it right? Sekejap. Bagi kan bukan dia dapat lagi tinggi ke? I don't know, sekejap. Kenapa dia pilih 30? Sekejap aku tanda ni. Hai. FA. Okay, sekejap Kena darab berapa? 2000 darab 0.08 160. There's no 160 there. Okay, tak apa. Ni tak payah dulu. Kalau nasi pening, boleh tengok textbook soalan tu. Dia ada beza sikit dengan yang final. Okay. FA over CO equals to 2 over 10. Okay, 0.2. 0.2. Dia cari sini kan. Okay, so dia guna deep groove lah. So dia pilih deep groove. Okay, dia ada sini juga, tapi ini lain tak? Ini lain. Oh, dia ada juga. Dia ada cylindrical roller bearings. Okay, sekejap sorry. See here. Ni in kilonewtons. Oh, betul lah. Kalau 2 tu darab 0 dengan 0.0. 2 darab 0.16. Okay. Okay. 3 bahagi 25. So cari something less than 25. Okay, dapat dah. Okay, so ni corresponds to the bearing designs. So FA kan kita 2 kN. So kita nak cari kita punya CO, it needs to be less than 0.08. So CO kita sekejap balik ke kita ni kan, ni darab CO okay, 2 bahagi 0.08. Okay, so we need to find something less than 25. Okay, so sini 25. So dia pilih 10. Kalau textbook dia suggest 10. So find something less than 25. So that is what this corresponds to lah. Okay, so far kau rasa dia macam ni, so dia tukar tak. Okay, so and then kita nak cari, so from there kita buat apa? From there kita dapat E tu table 11.1. Okay, so akan dapat dimensionless force ni, FA equals to 2 tadi, V equals to 1 sebab the inner ring rotation. Okay, V equals 1 sebab inner ring rotation. Okay, so 0.4. So dia kira lebih lah. So dia kira high load. Kita kira sebagai low load lah. Okay, sekejap. Kalau kenapa dia reverse ni? Okay, oh dia ada kat sini juga. Okay, kalau kat sini dia ada tadi 0.08 kan. Somewhere here kan. Somewhere here. So dia pilih 0.34 ke 0.38. Kan boleh pilih sini sebab dia beza sikit dia punya F over A dia. Oh, 0.2. I see. Okay, faham? Okay, sekejap guys. Aku tahu korang macam apa benda dia buat ni. Okay, so dalam textbook dia punya FA over CO is 0.2. Dalam finals ni is 0.8. So what does it mean? It means that kalau kita punya FA tu, kalau contohnya FA kita 0.2, kita nak cari CO kita, FA over 0.2, this also equals to berapa? 2 2. So 2 bagi tu is 40 dah kan? 2 bagi 0.2 10. 10. So that's why dia pilih CO to be 10. So okay sekejap ini textbook punya. This is, let me put here, this is for the textbook soalan, and kita dapat 25. So we need to highlight this. Okay, so this is the finals. Okay, so there's a quite difference there. And then they also say that kalau this is the textbook dia punya example dia is 0.2 kan. Kita punya past year is 0.08. So the E is supposed to be in between here. So okay, so from here kita tahu that E is 0.27 to 0.28. 0.27, 0.28. Okay. So determine the equivalent radial load that will be experienced. Okay, jap, sabar. Okay, and then we find FA over ni FR 0.4. So kita pun boleh buat macam tu juga. FA over V FR equals to 2, 1, FR kita 5. 2 bagi 5 berapa? 2 bagi 5 2 bagi 5 0.4 0.4 juga. Okay, so this is greater than E. Okay, kita bandingkan kita punya dimensionless ni dengan kita punya E. So sekarang ni kita dapat 0.4, E kita 0.28 ataupun 0.27. So FA over VFR is bigger than E. So that's one thing you can consider. So it is considered to be a high load high load. So kalau high load tu maksudnya dalam graph tu it surpasses the equals to one thing lah. So it's in this region. It's not in that region. Okay. So that is what they want to tell you. And then interpolate, obtain x2 ni, y2 ni. Okay. FE equals to x. Okay, so we use this equation x plus y. So kita nak kena cari x and y. Okay, so where do you find x and y? So we want to find FE equals to x plus y. Jadi kita ada FA over VFR. So kita cari from table 11 tu, table sini. See. So sekarang ni our case is it is bigger than E. So for here kita cari lebih kurang sini lah. So x2 kita equals to 0.56. Yang ni interpolate. Aduh, malasnya. 0.08. Let's just say it's like kita wing it 1.58 lah. Okay, nanti korang buat betul-betul lah nanti. Okay, so x is, okay, from here x is 0.56, y is 1.58. This kan kita dah cari tadi berapa? 0.4. Okay, 0.56 plus 1.58 times 0.4, it will be equals to, am I doing this correct? 1.5. Sorry. Dia guna ni. VFR tak FA. Okay, sorry. So VF darab dengan X, FA darabkan dengan Y. Okay, noted. So hold on. So this is not it. Padam balik. It's not supposed to be there. It's supposed to be FE equals to X darabkan dengan VFR tambah Y darabkan dengan FA. So we have 0.56, V kita 1, FR kita 2 plus Y kita 1.58, FE kita berapa? FE kita 2. Oh, ni 2. Sorry. 2. Ini 5. Okay, so what do we have here? So 0.56 darab 5 tambah 1.58 darab 2. 5.96. So FE equals to 5.96 kilonewton. 5.96 kilonewtons. That's the answer. Alright, so that is the first answer, guys. That is the equivalent radial load. So that is 10 marks. Oh my god, 10 marks. So state your key decision in making the selection of the bearing type. So what does that mean? It means that kita pilih kita pilih apa? Kita nak pilih deep groove ke kita nak pilih angular contact. So kat sini kita just assume 25 lah, 25. So we using deep groove. Deep groove. So state your key decision. I don't know, I just find the answer. Kau tulis tu deep groove bearing. Okay, so that's the first question. Second question, determine the predicted life in revolution per minute, RPM, that this bearing could be expected to give this application with 99% reliability. Okay, so RD equals to 0.99. Is that what I think so? Itulah 0.99. RD equals to 0.99. So this is where the Webull comes in. So this is where the... Okay, so maybe we can continue that later. Webull distribution. How many hours has it been? 1.5 hours. Oh my god, it feels like forever. Do you guys want to do it now? Sekejap apa sih kita buat je lah. Current template. Okay, let's go. Okay, so from the notes here, we know that the... Nak guna yang mana? Guna ni. Guna ni ke? Ke guna ni? Ni guna yang mana? Textbook guna mana? Textbook guna X plus tu over... Oh, dia suruh cari XD. Okay, so sini dia suruh cari XD. XD ni refers to the dimensionless life. Betul tak? XD ni refers to the dimensionless life. Korang tulis tu, dimensionless life. Okay, so kita punya mana tadi? Kita punya equation equation kita mana tadi? XD. Ni XD. So kita nak what do you call it? Kita nak extract XD from this equation. Okay, so how do we do that? We have C10 here. We can darabkan C10 with A and then move the whole thing to on the other side. Okay, I think this will have a better representation if I look case here. C10 would be kuasa A. Betul tak? Okay, let's try doing this. C10 will be kuasa A, AF over FD. Okay, AF FD ni kuasa A. So ini, okay, so you see AFD ni bawa on the left hand side, ni darabkan belah sana. So XO plus theta minus XO darab 1 minus RD. Panjang dia punya jangan kira. X apa tadi plus apa theta minus XO 1 minus RD kuasa 1 per B tak lah, let's see, 1 per B. Betul. Okay, and then just key in and then you find XD. Okay, so what is our XD? Come on, don't give up, keep it up. So C10 kita cari tadi. What is our C10 guys? C10 kita ialah 436. Okay, kalau textbook dia guna 19.5. Betul tak? See, textbook dia guna 19.5. Kalau kita, dia guna sini sebab tadi kita guna 10 kan. CO kita tadi kita 10, so dia guna 19.5. Kita 25, so kita cari 43.6. So kita punya C10 is 43.6. AF dia apa? 1. Oh, it's also given here kan, application factor. So we will just assume it to be 1. Okay, don't worry. 1. FD is the design. So what did they use? 5.34. Why? How do they find 5.34? Is it because based on over here? Macam mana dia dapat FD tu? Anyone know how he find FD? Kalau kat sini FD tu tak ada sini. Design load. Design load FD equals to over here LD over LR 1 over A. Okay, never mind. Kenapa dia guna 5.3? Okay, sekejap So sini dia guna 5.3. That is my question now. How do they find 5.3? Ni dia dah bagi, ni dah bagi, ni dah bagi, ni pun dah bagi, ni pun dah bagi. Okay, 5.3 For equation 1010 for SD. What is equation 1110? Do you guys know what is equation 1110? 1110. Sekejap, ada kat sini. Hold on. Where do they find FD? FD dia pakai FE kan nasi. FD tu equivalent to the load dia kan? Tak juga. Kalau ni load dia 2 dengan 5. Yang ni dia letak 5.34. Aku tak tahu mana dia jumpa, mana dia guna. Kenapa dia guna 5.34 tu? Sebab ni dia guna axial and radial. So probably there's something to do there. Tengah cari mana dia dapat FD. Ini lain. Shoulder diameter FD. Tak apa lah. Macam mana guna FD? Oh, kat sini dia guna FD sama dengan FE. Aku kata FD dia pakai FE kan? FE kita apa? Oh ni. Oh sini tu. Oh situ. Oh sini lah, sini. Oh okay. Thank you dah. Thank you. Shout out to Isaac. 5.96. Okay, so we're on our way. Theta dia berapa tu? Theta dia 4.459 minus 0.02 and 0.02 1 minus 0.099 1 over B dia 1.843 1.843. Okay, so ni kena kuasakan dengan A berapa? A sama dengan 3. Okay, cuba korang cari XD dia dapat berapa. Korang tengok ni. 4.36 over 5.96 kuasa 3 darab 9.02 tambah 4.9 minus 0.02 01 kuasa 1 over 1.893. Okay, aku dapat 22.8157. Lebih kurang tak? Lebih kurang. So XD equals to LD over LR. LD over LR. Okay. LD over LR. LR is equals to LD is equals to LN times 60. N is 400. Kita cari L tu sendiri. So L is equals to XD kita to 2.8157 times 10 power of 6 over 400 times 60. Okay. $9.50. Oh yeah, let's go. Dia dapat 400 for 4 hours. Kita dapat 950 hours. Kenapa kita punya live lagi lama? Sebab kita punya kita cari bearing type yang lagi padu lah. 0.08. So conclusion dia FA over CO yang rendah will have higher life. FA over betul lah, betul. Okay, betul. So sini dia bukanlah less than, sini betul lah, dia more than or equals to. More than or equals to. So to find a better bearing, you should find something more than this. So if they give you, okay, kita buat recap. If they give you F over CO equals to something and dot, you need to find something more than that. Kalau macam ni, dia kena cari more than this. Macam tu lah. So dia cari yang minimum. Kita pun cari yang minimum. Macam tu. So bigger bearing leads to a longer life. I think that's what they mean. Okay, so we can also include here bigger bearing, longer life. Okay, alright. Okay, semua faham tak? Semua faham kan? Okay. We still have halfway to go, man. Oh my god. Okay, lubrication. Is there any questions for the bearing tadi? Was I going too fast? I think I was going too slow. I was dumb. FD dia equals to FE sebenarnya. Oh, baru tahu. FD equals to FE. Okay. Ada sebarang soalan tak daripada chat? Thank you to Isaac for helping me. Okay, so kita teruskan dengan lubrication. Okay, lubrication ni dia guna Petrov's equation. Okay, so there are a lot of types of lubrication. Kita ada hydrostatic, hydrodynamic, electrohydrodynamic, solid film, boundary. Don't know what does that mean. Then we have viscosity. Kita ada banyak viscosity, tapi in certain formulas dia guna Z. So we have mu, absolute viscosity, we have tau, we have shear stress in fluid, we have this mu, we have kinematic viscosity. Selalunya yang ada dalam property table is the mu, the u, or the v, Okay, so here are some few parameters that we can find. First is the clearance. C is equals to D besar minus D kecil. D besar is the bushing over here, minus D journal over 2. Then we have the shear stress too, which is viscosity, U over H. U2 is the surface velocity, H2 is the height. So U2, U besar, capital U, surface velocity equals to 2 pi r times n. N besar is the rotation in RPM. So n besar ni is rotation. Kalau n besar dalam stress analysis tu is number of cycles. So bear in mind. So then we have surface area, 2 pi r times L. This is a basic surface area of a cylinder. This is power loss. H equals to 2 pi times n times t. N is the rotation, t is the torque. So W is also the load on journal or force applied, equals to 2RL. 2RL is referring to the rectangular area of the shaft lah. Dia count as cross sectional area of the shaft. I don't know why. And then dia dah P. P, pressure inside the bearing. Pressure inside the bearing. Okay, so these are the known parameters. And then we have the dimensionless parameters. So the purpose of lubrication is, you guys don't know still, protect the parts from foreign matter, provide a film of lubricant, distribute and dissipate heat, prevent corrosion. Okay, and then we have dimensionless parameters. First one being the bearing characteristic number. So this is important because it will be used in Summerfield number. U times n over P. Then we have radial clearance ratio, R over C. R is the radius of the shaft, C is the clearance. So if you have a bigger ratio, it means that the radius is bigger than the clearance. If you have a smaller ratio, it means that the clearance is bigger than the radius. Okay, I hope that makes sense. So this is a Summerfield. Okay, Summerfield 2 is just the ratio squared times the characteristic number. Okay, so this is Petrov's equation. This is like self-explanatory lah. This is all the variables, parameters. This is all the non-parameters. This is the calculated parameters. Okay, so first we have friction torque. Friction torque is equals to the shear stress times the area times the radius. So what you will derive is T. Dapat lah ni. And then we have another one which is torque juga, tapi is equals to the friction factor times the force applied times R, and then you will get this. So these two equations can be simultaneously simplified, and then you will find yourself F. F is friction factor. Friction factor. So friction factor ni equals to 2 pi squared times the Summerfield number. So ni dia just derivation daripada atas sampai bawah je. Cuma dalam exam tak pasti dia bagi equation apa. Kau kena derive sendiri ke apa ke. Ingat benda-benda ni. And then this is all the units. This is all the proper units lah. Okay. So lubrication ni, tu dia. Okay, tak apa. And then kita teruskan daripada screw. Lubrication ni ada soalan tak? Aku rasa macam lubrication ni doktor tak senang sangat. Ada lah satu kelas tu doktor sembang, tapi satu kelas je lah. You guys have any question for lubrication? If not, we continue to screw. Okay, so screw specifically for power screws. There are a lot of screws and there are bolts. Bolts, and then ada juga aku tak mention dalam ni. It's like an array of bolts. Macam ni, eccentric load. Eccentric load on bolt patterns, macam tu lah. Kalau bolt tu ada 4, bolt tu ada 3, ada stress analysis dia lah. Tapi kita tak cakap satu sangat lah. Kita cakap asal power screws ni. Okay, so power screws, we have collar friction. Collar friction tu, collar tu is the gasket. We can call it a gasket juga lah. Power loss, H equals to TW. W is RPM, T is the torque. Efficiency ni TO equals to TR if there is no friction. So efficiency is 100% if friction is ignored, but it's not. So TO over TR. TR is equals to FL over 2 pi. TR is over FL over 2 pi. And then we have self-locking mechanism where the friction factor is bigger than the length over pi dm. Dm tu apa? So kat sini aku tulis dm tu is, M is mean as in MENAN, MEAN, mean diameter, mean. R ni is the root. Okay, L tu is the length lah. L2 is the length, N times P. N is the number of, P is the pitch or unit, units pitch. Berapa banyak pitch yang dia dah masuk, macam ni dah lah. Then we have raising and lowering torque. Usually for screws, soalan memang guna raising and lowering torque. So there's TR, there's TL. TR for raising, TL for lowering. Primary difference is in the brackets. I don't know how they derive it, just ikut je. And I am sure that formula ni akan diberi lah. Aku tak hafal benda ni. F.dm mean radius, mean diameter ke mean radius, tak ingat. F is axial force, and then length plus pi FDM, pi dm minus FL. Okay, and then this is also vice versa. TR is using ACME thread. ACME thread ni is when the power screw has an angle. So power screw looks like this. ACME tu dia macam ada angle sikit macam ni lah. So this is the equation. Then we have stresses. We have shear stress tau 16T, which is torque, over pi d cos 3, dr, which is the root. Then we have sigma A, axial stress 4F, 4F pi d squared, radius of the root, ni the force. Then we have bearing stress, ni axial stress, ni bearing stress. So usually kalau sigma ni kita boleh assume sigma A as sigma X, bearing stress is sigma Y. And then moment over Z is the moment of inertia, which is here, moment of inertia. And then we have M, which is F dot P over 4. So over here kita assume that the stress element plane, the sigma X equals to bearing stress, the Sigma y is equals to negative axial stress. Axial stress kalau negatif dia compression lah kan. And ni 0 ni kita tahu shear stress lah. Shear stress. Okay. Transverse stress 3F over pi dRT. Okay, itu je lah untuk screw. Quite tu lah. I to lead N. I to lead N. I. Mana I? Sorry, Faris Fikri. Aish. I to lead L. L to lead N. L to length. L to length. L to length. Betul silap. L is length. Mana screws? This screws. Sekejap. Dia cakap sini. Sekejap kalau orang tanya L tu apa, just making sure. Length. Sini tulis length. Sini pun length. Aku rasa length lah. Sekejap kita confirmkan. Ni L equals to NP. What do you mean L is lead? What you mean, bro? L. Okay. Itulah L. Okay, anyway. So, ada kat slide tadi. Slide mana? Slide aku ke slide textbook? Yang L equals to NP. L equals to NP. Ni length. Number of textbooks. Number of pictures. Aku ada tulis kat sini juga. So, I think you're right. Mana? Lost. Aku rasa nampak lagi. Textbook 8.1. Oh no. Example 8.1. Betul lah sini. Okay. Okay guys, sorry. With double threads. Double thread. So n equals to 2 lah. Macam tu Okay. Number of threads. Tulis ni, number of threads. Ini pitch. Okay. So now kita tengok ni friction coefficient and pressure for the pressure apa? For the power screw kan. Ni untuk power screw. Yang table 2 ni untuk power screw. Okay, now kita masuk gear. So we have spur gear. How long has it been? It's almost 2 hours. Okay, so gear pressure angle. We have pressure angle. Usually pressure angle is equals to 20 or 25. And then we have tooth size, diametrical pitch, capital P or lowercase p, circular pitch, pi d over n or pi m. M is module, which is pitch diameter over number of teeth. So that is module. Then we have contact ratio. Contact ratio MC equals to QT over P. P is in the lowercase p. R of action, I do not know what is this. It's just in the textbooks. And then there's interference. Interference happens when the gear tips langgar kat bawah, not where it's supposed to be lah. It's below it's exceeds the line, something like that. Interference. So it's not good. Interference not good. Okay. So we have train value. Train value is like you have an array of gears. How would you like to find the overall gear ratio? So E is the overall gear ratio, and F is the first gear, L and L is the last gear. Compound gear is what is like this. And then dia macam kecil and macam tu. That is the compound gear lah. Okay. So this is the forces acting upon a gear. We have the forces coming from 3 acting on 2. Okay. So that is what it means. F32 means force coming from 3 acting on 2. Macam tu. This is the radial force. This is the tangential force. This is the radial. This is the tangential. And this is the torque. This is the torque. This is the torque. This is gear number 2. This is the diameter. This is the reaction forces on shafts. This is the reaction forces on. This is RS and RY. You can say anything you want. Okay lah. And then we have stress analysis of the gears. Torque is usually diameter over 2, which is the radius of it, times WT, the tangential load. Then we have power or power loss. We have H equals to T omega, the rotational speed, which is also equals to D over 2 WT times omega. And then we have WT. What is WT? In kilonewton. This is in kilonewton. This is in kilowatts. So how do you want to change from kilonewtons to kilowatts? Darabkan dengan 60,000 bagi dengan pi d darab n. N is the speed of rotation, d is the diameter. Pitch line velocity is where usually the tip of the gear moves. Macam tu lah. V equals to pi d n over 12. Okay. So that is all for gears. We have one question in the past year regarding on gears. So let's do that, I guess. Oh, are you guys still there? Do you guys have any question before I proceed the past year question for question 3? Okay, so we have figure 3. Oi, baik doa kid. Adam. Thank you the kid. So we have conventional gear reducer with an idler. Gear reducer referring to the overall gear ratio to be less than 1. I think first gear betul lah. less than 1. All 3 meshing gears should show in here. Pressure angle, blah, blah. Okay, so now we have E to be less than 1. We have M. We have pressure angle. M is 5 millimeters. 5 millimeters. We have 20. And then what do we have? Driving gear 1 transmits 40 kilowatt of power at regular to located on shaft B. I will use shaft C. Drive the machine. Draw a free body diagram of gear 2 and all the forces acting on it. Then calculate the tangential and radial forces acting upon it. Based on your drawn free body diagram, verify what is the purpose of an idler for this setup. Si kalau design kan, dia tanya kau soalan kau, dia tanya kau balik, kenapa ada idler ni? Okay, what is the reaction force on shaft B? Oh my god. Okay, so aku rasa reaction force ni kita ada pernah buat tau. Sekejap mana reaction forces? Okay, pitch diameters, torque forces on each gear shown on the free body diagram, results turn force of the shaft of gear B. Lebih kurang sama ni soalan dia. So okay, we know that M equals to dt. M d teeth. Do we know how much teeth there is? Oh my god, we know. Damn. Okay, so dA equals to m dot t. dA equals to m dot t. dB equals to m dot dB dc. Do you guys want to do this? Okay, let's just do this. Aku dah ngantuk gila. Welding tu, parallelogram method ni kan, dia very payah tau. Sebab kau kena make sure korang punya angle tu betul. We'll get to that later lah. Just saying. So M is berapa tadi? 5 5 times berapa? 2A ni. A is 20. Then we have 40. Another one. And then we have 30. And another one. 5 times 20 is 100. This is 200. This is 150. This is the diameters. Alright. Okay, so now we need to find the torque on gear A, torque on gear B, torque on gear C. So torque on gear A, we know that torque is equals to, mana tadi kita punya notes, kita try guna notes kita. We do not have torque here. D over 2 WT, tangential load. Tangential load ni kita assume it to be berapa kilonewton tadi. Dia ada bagi dia bagi kilowatt. So kilowatt to kilonewton, kita kena guna something. Kita guna Kan dia sini dia bagi, dia tak bagi kilowatt, dia bagi kilonewton. See, WT equals to H 60,000 over pi dn. Oh, diameter. Okay, so we using the A diameter, speed. Okay, faham? Okay, so we have WT equals to 60,000 H over pi dn. Okay, so we have 60,000 times how much kilowatts? We have 40 kilowatts. We have 40 kilowatts over pi d of A. Kita assume this to be A, 100 milliliters. 100 milliliters times n. N is 200 rpm. As it wants to be in radians per second or just minute? 200 rpm. Okay. Kat sini dia tak tulis tau. Usually dia memang guna rpm. Kan dalam ni pun dalam ni pun dia tulis ni rpm and diameter. So you guys don't need to worry about the units lah, sebab dia memang H as kilowatt, speed as rpm, diameter as millimeter. Okay, so what would we get? Okay guys, cuba korang cari load. 60,000 times 40 bagikan dengan pi times 100 times 2000 rpm sebenarnya. 3.8197 kilonewtons. Alright, so dah jumpa dah. So let's see, do we remember D over WT? H equals to, not H, not T. D over 2 WT. Torque equals to D W2 over 2 WT. So torque is equals to 100. Kalau bagi 2, 50 milliliters. 50 millimeters. WT is in kilonewtons. And we will get 3.8197 kilonewtons. So torque would be in newtons. 50 times 3.8197. You will get 190.985 newtons. Okay, so that is the torque. Okay, so TA equals to Newton meters. My bad. Newton meters of TA. TB kita kena cari tak salah aku 200 kan. 200 bahagikan dengan 2 darabkan dengan 3.8197. You will get TB ni kali 2 je lah kan. Does it make sense? So there's more torque. Are you sure? You sure, bro? Oh, there's a different angular velocity. Betul? Different angular velocity. Sekejap tengah tengok balik ni. Oh, TA over TB equals to, wait a second. Kita cari TA je lah. FTA equals to TA over pi A. Pi, what is that? What is that? Pi. Okay, sekejap aku nak buat apa, free body diagram. Okay. Kalau free body diagram of tu, I think this is what it's referring to. I don't know. That is the most serious thing I ever seen. Oh my god. Okay. June. FT. Okay. So dia macam tu, and then dia keluar, then dia tahan. So dia macam tu, lepas tu dia keluar. So dia macam tu. And then kalau ni, dia macam tahan tu, and then dia tahan macam tu. Betul. Betul. Okay lah. So this is FR, FT, FN. Is FR, FT, FN. Normal, tangential and radial. Macam tu. Korang kena buat macam tu. Okay, lepas tu FT, RA. Korang kena buat ni pula. Aduh, 0.125 apa ni sebenarnya? Pressure angle, RPM. Oh, vertical load. Oh, okay, faham. Okay, so kalau bulat and dia dapat load daripada sini, and dia dapat load dari sini, cuma sini dia akan dapat masuk, so dekat shaft dia ni, dia akan dapat equivalent force to the side here. Macam tu. So based on the assignment here lah. So cuba cari FY tu berapa. Nak buat ni tapi macam malas. Okay, tak payah buat. Okay, kita teruskan lah. Kita teruskan pada welding. Okay, semua okay ke? Aku rasa gear ni dia punya tu agak leceh lah. Tapi korang faham kan gear ni? Dia FTT over ni dia punya distance. 0.1, 0.125. Ni R ke? Buat betul-betul lah say. Apalah 0.1 meters you mean? Oh betul lah, meters. Betul. This is meters. C meters. STT over R. Boleh juga. Okay, F equals to, sekejap sabar. Okay, kita try buat TA ni lah. FA equals to TA over RA. So TA is 190.985 over diameter dia ni Newton meter kan. Newton meter, so bagi dengan meter lah. 0.05. So you akan dapat F dia as 190.985 bagi 0.05, 3.82 kilonewtons. Okay, so we know that FA equals to FTA, tangential. Normal equals to NA. How do you find this? Like cos theta. Oh, that is where the pressure angle comes in place. FNA. Oh, okay, faham. So pressure angle, so ni FN. FN. Ini FT. Ini FNA equals to FT over cos theta. FTA over cos theta. So tadi kau dah dapat jawapan tu. Cos kita 20. So ni 38197 equals to bahagi dengan cos 20. Is this in degrees? Yes, it is. 4064.8 kilonewton. Newton. 4.06 kilonewton. So tu FNA. Kalau FNA, kalau FRA equals to FNA times sin theta. FNA sin theta. So FNA sin theta is 4040664.8 sin 20. So akan dapat kalau sin 20 1.39 kilonewtons. Okay, so 1, 2 and 3. So bolehlah tanda kat situ. FTA equals to berapa? NA berapa? FRA berapa? Macam tu. So akan dapat the conclusions of FRA kuasa 2 tambah FRC kuasa 2 untuk dapatkan ni. F kuasa 2. I think so. Sebab base over here dia macam tu. FNA cos theta cos 45. FNA cos 45 ke bawah. Tu. Sebab tangential dia akan transfer. So net load on tu dia akan jadi net load. Sekejap. Ini dia akan jadi FRA FLC tu. Dia ada beza ke? Dia sama je. Oh, dia beza. TC tak tahu C dia punya tu berapa kan. Macam mana dia cari tu Sekejap guys. Power transmitted. Aku rasa something like TC over TA equals to dia punya number over number. Sila. So kalau kita nak cari TC over TA, kita tahu yang number of A ni is apa? 20. Ini 30 so TA ni, so kau akan dapat TC as you guys akan dapat as 190.985 times 2 bagi 3. Sekejap guys. 127.32. Supposed to be lower. Is it? Ini 57. Ni 45 betul lah. The lower tu high top lah. Make sense. Okay, this is korang boleh guna equation ni kalau korang boleh guna equation ni kalau korang nak tahu torque. So contohnya kau nak cari torque C kan, TC over TA is equals to the NA over NC. So because they are directly related to the number of thieves. So dari situ kalau FRC FNA sin theta. Okay, tak apalah, ini cari sendiri lah. Cari sendiri. Okay, so now kita sambung welding. Okay, welding kita ada primary shear dengan secondary shear. So kita berapa jam ni? 2 jam 20 minit. Okay. So primary shear force tau equals to V over A, direct shear over throat area. And then we have secondary shear, M moment, R distance, J second polar moment. Okay, so these are some of the bending properties. Kalau kau perasan, bending properties guna I. Ni torsion properties guna J. Usually kita akan guna torsion properties. Then kita ada strength properties here. And then we have allowable stress. Allowable stress equals to 0.3 SUT for most of our applications, sebab kita fokus on fillet. Setakat ni semua welding yang kita buat semua fillet lah. So mostly T allowable equals to 0.3 SUT. Okay, so okay, kita explain pasal normal method. Normal method ni dia akan bagi kau dimension semua, and then there's V is the load, then there's A is the area, also given here. Throat area ni dia dah bagi. Okay, and then find the primary shear. Okay lah, so guna equation tadi kau akan dapat. Ni contoh soalan tau aku ambil. Just nak display the difference between normal method and parallelogram method. Then kau nak kena cari M tu. M, R, also J. J ni dia beza dengan JU. So J, okay, so most of us tengok sini dia dapat JU kan, dia bukan J saja. So JU, and then darabkan dengan 0.07 H darab JU. Macam tu. Okay, so itu penting. So darab dulu. So kau akan dapat J ni equals to 1.532. And then you use the secondary shear to find the tau, and then you will get Y components and X component, because kalau normal method R dia ada RX dengan RY. Kalau parallelogram method dia tak ada RX RY, dia just R. Yeah, okay, and then you have tau max equals to punca kuasa 2 ni tambah ni. Sebab apa? Sebab sini lah tau max. Kan sini is the center. This is the center. So TX is cancelled out. So what is left is just T double prime X, tau double prime X, tau double prime Y, and tau Y prime. So that is the reason why the T max looks like this. Okay, I hope that helps. And then we assume that the T max equals to the T allowable, and then you find your final force. Macam tu. Okay, so for the parallelogram, kita kena cari radius distance dia lah. Rx over bukan Rx lah, dia basically macam kau cari hypotenuse lah, hypotenuse. Ni guna Pythagoras theorem. Then the primary shear would be V over A. V is the load. A dah jumpa dah tadi. Secondary shear, kita dah jumpa R, tak ada komponen X ataupun Y. So darab je 3.3, 33.F. Okay. So this is where the parallelogram enters. This is where it is different, because dia ada banyak angle. Okay. So first is alpha. Alpha is the angle between the tau double prime B, because tau double prime B is moment. Moment dia macam perpendicular to the radius, macam tu. Kalau kalau yang tau prime dia ke bawah ataupun ke atas ataupun kiri kanan, sebab dia depend on the load. Depend on V. Senang nak ingat, yang ni dia depend on V. Yang ni depend on M. So M kan dia kan kena perpendicular to the radius kan. So that is why it has a special angle. Kalau tau prime satu je tak ada. Okay. So from there we need to find beta. So beta dia beza untuk TB dengan TC, sebab kat sini kita assume that the forces for for joint at A and joint at B is the same, sebab it looks the same. Dia macam dia ke bawah macam tu je, dia punya parallelogram dia. Tapi kalau C dengan D, parallelogram dia lain. So dia macam tu. Dia macam tu. So kita assume yang kita assume sini lah. Kita assume TA equals to TB, TC equals to TD. Macam tu. Okay. So untuk yang TB, I dah buat macam ni. Beta equals to 90 degrees minus alpha over 2. Tapi kalau ni 180 degrees minus alpha over 2. You guys can do your maths by your own. So and then from there you cari beta ni. You need to find beta to use in the cosine rule. Cosine rule ni jangan lupa, sebab I don't think they're gonna give this cosine rule in the exam. So you'll find T max, T max squared. Then only then you can use it to find the force, which is over here. Macam ni lah, lebih kurang macam ni lah juga. Okay. So I think that's all for design machine element under 2 hours and a half. Do you guys have any question? Boleh nak request guide macam mana nak lukis FBD untuk welding, sebab tak faham sangat nak lukis arrow tau prime dengan tau double prime tu. Okay. Boleh. Okay. So right now, contohnya kita ada center. Okay, ni contoh fillet well. Okay, ni contoh fillet well. So fillet well ni, the well itself will only be 2 sides. Okay, so one side on top, one side on the bottom. Okay, so this is the center kan. Okay, so for tau prime, it usually uses V over A. So V ni, it is used for the load. Macam contohnya kat sini kita introduce F. Okay, F. So you're gonna have 1, 2, 3, 4. Okay, why are those 4 corners chosen? Because those 4 corners are the furthest from the center. So usually the stress on the furthest of the corner ni paling tinggi, sebab top dia tinggi, something like that. Okay, so that's why kita kena ambil the bucu dia sebab this is where it is furthest from the center. Why we choose it? Because it's furthest from the center. So contohnya kita bagi loading F. So kat sini dia akan reaction force. So all of those 4 points will react to the given force, macam tu. So dia akan ada ni, contohnya A, this is B, this is C, this is D. Okay, so FA plus FB plus FC plus FD equals to the F lah. So F, so FA equals to, contohnya kalau kita assume semua sama, 1/4 F. Okay, so that is F is what V is lah. So this is corresponding to the V. So that is why it is usually just straight up ataupun tepi. Kalau tepi, contohnya macam mana? Contohnya macam mana ni? Kalau ni macam tu, tolak macam tu ke? Dia bagi moment. Kat tengah tu dah memang ada moment. Jap. Contohnya dia bagi F macam tu, ataupun so the 4 points would be opposing it. So dia akan jadi macam tu. So this is for the first tau, macam tu. But usually dia akan guna ni lah. So basically most of the tau forces are up or down, macam ni. So tau double prime dia related to moment. So moment ni dia tak ada R. So kalau ada 4 point tu, dia nak cari yang perpendicular, faham tak? Forces perpendicular to the radius. Sebab macam mana nak cakap, kalau ni F, ni R, M equals to FD kan, ataupun FR. Torque lah, macam torque. FR kan. So kita assume the shortest distance, bukan shortest distance lah, the maximum moment. Keyword dia is the maximum moment is at the corner of the welds, and also the force is perpendicular to the center. Macam tu lah, perpendicular to the center. So kau kena lukis diagram kau macam tu. Kalau macam ni, dia akan ke atas. Okay, kenapa dalam direction tu is because force ni dia akan introduce a bending moment. Bending moment. Kalau force tu dari bawah, okay, contohnya kita buat pelik sikit. Force tu dari bawah, dia akan introduce a moment ke atas. So the forces will not be like this. The forces will be like this and like this. So tu je primary difference dia. So in the end, apa yang kau akan dapat dekat point A contohnya, kau akan dapat satu ke bawah and satu ke tepi. Sebab ke tepi ni dia macam campur darjah dengan tu. So angle ni, angle tu dikatakan sebagai alpha. Alpha tu boleh dijumpa oleh cari yang aku bagi tu lah. Cuma kat sini lah. Okay. Ada apa-apa lagi soalan? Thank you Adam for asking. I hope that cover a lot lah. Most of it, I think. Hey, thank you for watching my stream though. I have concurrent views of 16 people watching this. I am very proud of you. I hope you will succeed in your finals tomorrow. Thank you guys. So, is there anything else before I end this stream? Let me. Alright. Bye guys. Thank you for watching my stream. I really appreciate it. I hope you guys have a very successful exam tomorrow. I hope so. Happy to help. Any questions, just ask me away. Alright. Bye semua. Thank you. Bye. Amin. Let's go.